These are the answers to the AP Chemistry packet on topics 9.8 to 9.11. This is MCQ Practice, which means these are multiple choice questions for you to practice so you can prepare for the AP Chemistry exam. In the video description area, there is a link to the packet that accompanies this video. Now, let's take a look at our first multiple choice question. In question 1, we are given a diagram of a standard galvanic cell, and we are also given a table in which two reduction half reactions are listed along with the standard cell potential for each half reaction. The question says, a student sets up a standard galvanic cell with lead, Pb, and magnesium, Mg, as shown in the diagram above. Standard reduction potentials for the half reactions associated with the galvanic cell are given in the table above. The student fills the salt bridge with a solution of potassium nitrate, KNO3. And the question asks, which of the following is the correct description of the movement of potassium ions in the salt bridge as the cell operates? And we can see that in all four choices, they begin with the phrase, potassium ions flow toward, but then we have to decide, is it the lead half cell compartment or is it the magnesium half cell compartment? We also have to decide, are these potassium ions flowing toward the half cell in which oxidation occurs, or are the potassium ions flowing toward the half cell in which reduction occurs? So this particular question definitely falls under topic 9.8, galvanic and electrolytic cells. And one of the essential knowledge statements that I will highlight on this slide is the one that says, for all electrochemical cells, oxidation occurs at the anode and reduction occurs at the cathode. From my video that included topic 9.8, I talked about the movement of both the negative ions or the anions as well as the positive ions or the cations within the salt bridge. So on this slide you can see a summary of that information. So the negative ions or the anions, they move toward the anode half cell compartment, and they do that in order to balance the buildup of positive charge in the anode half cell. And you can see that from that half reaction that's listed on the left side of this slide, that would be the anode is where oxidation occurs. So you can see there's going to be a buildup of positive charge, so the negative ions are moving toward that anode half cell to maintain charge balance. There's also a maintaining of charge balance for the flow of the cations. So on the right side of the slide, you can see that the cations, or the positive ions, they move toward the cathode half cell, and that's where reduction occurs. So in that particular half cell, there's a loss of positive charge associated with the process of reduction. So the positive ions are moving toward the cathode to maintain charge balance. Now, with respect to anions moving toward the anode and cations moving toward the cathode, remember that oxidation occurs at the anode, reduction occurs at the cathode, and on this slide, it's a simple mnemonic device to help you remember the site of oxidation and reduction. So that phrase, an-ox and red cat, helps you to remember that oxidation occurs at the anode and reduction occurs at the cathode. Now, back to question 1, we know that potassium nitrate contains positive ions and negative ions. So the potassium ions are positive, so K+, the nitrate ions are negative, so NO3-, and so the cations, or the potassium ions, will flow toward the cathode. And the cathode half cell compartment is where reduction occurs. Now let's consider which choices in question 1 we can eliminate, since we know that the potassium ions are flowing toward the site where reduction occurs. So choice A and choice C indicate that that is where oxidation occurs, so we can eliminate those choices. We know that the potassium ions are flowing toward the cathode, where reduction occurs, so the correct answer is either B or D. All we have to do now is decide, is lead classified as the cathode, or is magnesium classified as the cathode? To figure out which is which, this would fall under topic 9.9, cell potential and free energy. So for a galvanic cell, which is thermodynamically favored, that is like a battery where that reaction is occurring all by itself. It doesn't require an externally applied power source like electrolysis. So therefore, we are looking for a positive voltage with a thermodynamically favored reaction that takes place in a galvanic cell. So I'm going to add these two half reactions together in such a way to get an overall positive cell potential when the two half reactions are added together. I need one of these half reactions to remain unchanged. So I'm going to start with the lead half reaction. I'm not going to reverse it. I'm just going to rewrite it exactly as is. So there is lead 2+, gaining 2 electrons to form solid lead. And the cell potential is negative 0.13 volts for that particular half reaction. But since I can't have two reduction half reactions, and obviously I can't have two oxidation half reactions, I need one of each. I need one reduction and one oxidation. I'm going to reverse the magnesium half reaction. You'll notice that right now in the table the cell potential is negative 2.37 volts. But if I reverse this half reaction, now the cell potential for that half reaction has been flipped from negative to positive. So it is positive 2.37 volts. When I add these two half reactions together, the electrons cancel out on opposite sides of the equation, and I get an overall balanced equation for this redox reaction that occurs in this standard galvanic cell. So we do have a positive cell potential, positive 2.24 volts, but more importantly, we need to figure out, is the lead or is it the magnesium that is the cathode? Remember that reduction takes place at the cathode. So lead is changing from positive 2 on the left to 0 on the right. So lead is being reduced from positive 2 to 0. On the other hand, magnesium is changing from 0 on the left to positive 2 on the right. So magnesium is being oxidized. I know I'm looking for the site at which reduction occurs, so lead is the cathode because it's being reduced, and that makes choice B the correct answer. Potassium ions flow toward the lead half-cell compartment in which the reduction half reaction occurs. Okay, well, the correct answer to question 1 is choice B. Now let's take a look at question 2. Question 2 says the following. The standard reduction potentials of the half reactions associated with a galvanic cell are listed in the table above. So the first half reaction listed involves the element silver, which has the symbol Ag, and the second half reaction listed involves the element chromium, which has the symbol Cr. And question 2 asks, which of the following shows the correct values for the standard cell potential, which has the symbol E0, as well as the standard Gibbs free energy change, which has the symbol delta G0. So which of the following shows the correct values for the cell potential and the Gibbs free energy change for the overall reaction that occurs in this standard galvanic cell? So question 2 falls under topic 9.9, cell potential and free energy. So reactions are either thermodynamically favored, resulting in a positive voltage, or thermodynamically unfavored, resulting in a negative voltage and requiring an externally applied potential. So because it's a galvanic cell, the reaction in a galvanic cell, like a battery, is thermodynamically favored. The sign of the cell potential should be positive, and then the sign of the free energy change, delta G, should be negative. So there's that relationship at the bottom of this slide. You can see that last essential knowledge statement has an equation. Delta G equals negative N times F times E. That is definitely an equation we'll be using to answer question 2. Now, because all 4 choices listed in question 2 have a positive sign of cell potential and a negative delta G, we cannot eliminate any of the choices simply based on sign. So our next strategy is to use these guidelines for manipulating half reactions. Now, these were the guidelines I had mentioned in my video for topic 9.9. So when combining two different half reactions to produce the overall equation for a redox reaction, the total number of electrons gained should be equal to the total number of electrons lost. We saw this back in question 1, where lead was reduced from +2 to 0, and so that was gaining 2 electrons, but then magnesium was oxidized from 0 to +2, and that was losing 2 electrons. So we definitely have to make sure that the electrons lost are the same as the electrons gained. Also, as we saw in question 1, if a half reaction is reversed, then the sign of the cell potential for that half reaction would also be reversed. And an important note, which is a very common mistake that students make, multiplying a half reaction by a constant n, whether that's 2 or 3, does not change the value of the cell potential. All right, so what I'm going to do is I'm simply going to write the first half reaction involving silver. I'm not going to change that half reaction. So it's going to be Ag plus 1 electron to produce Ag solid. So we're going from the aqueous silver ions to the solid silver. I'm hoping to get a positive cell potential, and right now that is positive 0.80 volts. But of course you can't have two reduction half reactions and you can't have two oxidation half reactions. You have to have one of each. Since I didn't change the silver half reaction, I'm going to reverse the chromium half reaction. So now it's going to be solid chromium on the left and then the aqueous chromium 3+ ions on the right. But notice in these two half reactions, and by the way, I did change the cell potential from negative 0.74 to positive 0.74. So that's good. That's going to give me a positive cell potential when these two equations are added together. But notice that I have 1 electron for the silver half reaction and I have 3 electrons for the chromium half reaction. I am going to multiply the silver half reaction by 3, but as I mentioned, you do not multiply the cell potential by 3. That cell potential will remain 0.80 volts. So now my coefficients in the silver half reaction will be 3, 3, and 3. Now I've got 3 electrons on the left and 3 electrons on the right, so that when I add these two half reactions together, the electrons will cancel out on opposite sides of these different equations. So my overall balanced equation for the reaction that occurs in this standard galvanic cell involves 3 moles of aqueous Ag plus ions reacting with 1 mole of solid chromium, and then the products of this reaction are 3 moles of solid silver and 1 mole of aqueous chromium 3+ ions. The standard cell potential would be the sum of 0.80 plus 0.74. So we definitely have a positive cell potential for the reaction that occurs in this standard galvanic cell. Let's take a look at our 4 choices. Positive 1.54, that means that the correct answer to question 2 is either choice A or choice B. So I'm going to go ahead and cross off choices C and D because the cell potential should be 1.54 volts. Now let's move on to the process of calculating the value of the standard free energy change, delta G, now that we know that the cell potential is 1.54 volts. So on this slide, here are some guidelines that I had presented in my video for topic 9.9 involving the equation delta G equals negative N, which the variable N represents the total number of moles of electrons transferred in the overall balanced equation for the redox reaction, times F, so that capital F is the Faraday constant, which is equal to 96,485 coulombs per mole of electrons, and then finally the standard cell potential, which has the symbol capital E, E naught, or E with that superscript 0, kind of like a degree symbol. Also, when you do multiply coulombs times volts, you get joules. So 1 volt is equal to 1 joule divided by 1 coulomb, and therefore 1 joule is equal to 1 volt times 1 coulomb. And the units of delta G are normally in kilojoules per mole, so we have to divide by 1,000 when we go from joules to kilojoules. Okay, so here's the calculation. We have 3 moles of electrons on the left, 3 moles of electrons on the right, so the value of N is 3. There are 3 moles of electrons transferred. My Faraday constant, 96,485, with units of coulombs per mole of electrons, and then my cell potential. The standard cell potential for this galvanic cell is positive 1.54 volts. So when I do this math, negative 3 times 96,485 times positive 1.54, I get negative 445,760.7. I'm going to round this off to 3 significant figures based on the cell potential of 1.54. The number 3 is an exact number, so that's not a measurement. And I get negative 446, but my units are joules. Joules per mole of reaction, because a coulomb times a volt is equal to a joule. To go from joules to kilojoules, I'm going to divide by 1,000, so I get that the delta G for this reaction is negative 446 kilojoules per mole of reaction. Well, now that I have that value, that means that the correct answer to question 2 is choice B. We have a standard cell potential of positive 1.54 volts, and we have a value for the standard free energy change, delta G, of negative 446 kilojoules per mole of reaction. All right, now let's take a look at questions 3 and 4. So we can see that questions 3 and 4 refer to the following information. It says a student sets up a standard galvanic cell with silver, Ag, and copper, Cu, as shown in the diagram above. Standard reduction potentials for the half reactions associated with the galvanic cell are given in the table below. And question 3 asks, which of the following statements identifies the electrode that decreases in mass as the cell operates and correctly explains why? So we can see that choices A and B indicate that the silver electrode decreases in mass and gives a different explanation. And then choices C and D indicate that the copper electrode decreases in mass, and we have 2 different explanations. So a good strategy for answering question 3 is to come up with the balanced chemical equation for the reaction that occurs in this standard galvanic cell. Because once we write this overall balanced equation for the reaction, we can determine which of the electrodes should be decreasing in mass. Now remember that a standard galvanic cell is thermodynamically favored. Therefore, the sign of the cell potential should be positive. So when we combine these 2 half reactions, we need the sign of the cell potential to be positive. What I'm going to do is I'm going to just write the silver half reaction without changing anything. So it's going to be 1 mole of aqueous silver plus ions reacting with 1 mole of electrons to produce 1 mole of solid silver. But since I didn't reverse or change the silver half reaction, I'm going to reverse the copper half reaction. You can't have 2 reduction half reactions. You can't have 2 oxidation half reactions. You have to have 1 of each. So right now, silver is being reduced. And when I flip or reverse the copper half reaction, now copper is being oxidized. Now, when I did reverse that half reaction for copper, I changed the cell potential from positive 0.34 volts. Now it is negative 0.34 volts. But if I add these 2 half reactions together, the overall cell potential will still be a positive number, and that's what it should be. Notice that I have to get the electrons to cancel, and right now I have 1 electron for the silver half reaction and 2 electrons for the copper half reaction. So I'm going to multiply the silver half reaction by 2, but I am not going to change the value of the cell potential for that half reaction. It's going to remain as positive 0.80 volts. So now my coefficients will be 2, 2, and 2. I didn't change the cell potential, and when I add these two half reactions together, I've got 2 electrons on the left, 2 electrons on the right, so I can cancel them out. And my overall reaction for my equation, my balanced equation, is 2 moles of aqueous silver plus ions reacting with 1 mole of solid copper, and then it produces 2 moles of solid copper and 1 mole of aqueous copper 2 plus ions. Is my standard cell potential for the overall reaction positive? Yes. Positive 0.80 plus negative 0.34 still gives me a positive value. It's 0.46 volts. With respect to the silver or the copper electrode, which of these electrodes should be decreasing in mass as this galvanic cell runs? Well, silver is changing from an aqueous ion to solid silver. So the silver electrode is actually going to increase in mass as aqueous ions are turning into solid silver. On the other hand, the copper electrode is changing from a solid to aqueous ions. So atoms of solid copper turning into aqueous copper 2 plus ions, that is why the copper electrode, its mass, should decrease. Let's go ahead and take a look at the correct answer to question 3. It's not the silver electrode that's decreasing in mass, it's the copper electrode. Is it because copper has a smaller molar mass than silver? No, the correct answer to question 3 is choice C. The copper electrode should be decreasing in mass as the cell operates because atoms on the solid copper electrode are oxidized to form aqueous copper 2 plus ions. And again, we got that information by writing the overall balanced chemical equation. So we can see solid copper on the left and aqueous copper ions on the right. So the correct answer to question 3 is choice C. Now let's move on to question 4. As you can see in question 4, it says, what is the value of the standard cell potential for this galvanic cell? When we were trying to solve question 3, we've already done this work. We've already combined the two half reactions together, so we already know the correct answer to question 4. The standard cell potential for this galvanic cell is positive 0.46 volts. So that makes the correct answer to question 4 choice A. Okay, now let's move on to questions 5 and 6. So we can see that both questions 5 and 6 refer to the following information. It says, the standard reduction potentials of some half reactions are given in the table below. And in question 5, it says, of the following equations, which represents the reaction that has the greatest thermodynamic favorability? So how can we determine which of these 4 choices would represent a reaction with the greatest thermodynamic favorability? Remember that we're looking for a sign that is positive for the cell potential. So the reaction in a galvanic cell is thermodynamically favored with a positive cell potential and a negative delta G. If we can calculate the cell potential by combining these half reactions in various ways, then we can make our choice for question 5 based on the following criterion. The reaction that has not only a positive sign for cell potential, but the one that has the largest magnitude of cell potential, that reaction should be selected as the correct answer. So I'm going to start with choices A and B. And we can see in choices A and B, they involve aluminum, Al, and rhodium, Rh, which means we have to combine the first half reaction listed in the table with the last half reaction listed in the table. Now, since I'm not sure which of these half reactions should be reversed, I'm going to go ahead and just make a choice and see what happens. So I'm going to leave the aluminum half reaction unchanged, which means it would be aqueous aluminum ions on the left, solid aluminum on the right, with a cell potential of negative 1.66 volts. Now for the rhodium half reaction, since I didn't change the aluminum, I'm going to have to reverse the rhodium half reaction, because I would need one of each, one reduction and one oxidation. Now, when I reverse the rhodium half reaction, now I have solid rhodium on the left and aqueous rhodium ions on the right. But look at what I did to the cell potential for the rhodium half reaction. It was listed as positive 0.80 volts, but now because I reversed that reaction, it is negative 0.80 volts. If we combine these two half reactions written exactly as they are, I would get a negative value for the cell potential, which means it would not be thermodynamically favored. So I can eliminate choice A, which shows aqueous aluminum ions on the left and aqueous rhodium ions on the right. Let me go ahead and switch around my choices. So this time I'm going to reverse the aluminum half reaction. That's going to put solid aluminum on the left and aqueous aluminum ions on the right. I had to reverse the cell potential. So now instead of negative 1.66, it's positive 1.66 volts. And then for the rhodium, I will leave it unchanged since we can't have two reduction half reactions or two oxidation half reactions. I'm going to reverse one of them, not both of them, but just one. So this would give me a reaction in which I have aqueous rhodium ions on the left and solid rhodium on the right. The electrons would already cancel out. I have 3 electrons on the left and 3 electrons on the right. And when I combine these two half reactions together, this looks like the reaction written in choice B. So what's the cell potential if I'm combining these two half reactions? Positive 1.66 volts plus positive 0.80 volts. That gives me a value of 2.46 volts. So right now I can see that choice B could potentially be the correct answer, but I have to consider what happens in choices C and D. So now let's take a look at choices C and D. In choices C and D, we are combining the copper half reaction, so copper is Cu, with the rhodium half reaction. Since I'm not sure which one should be reversed, I'm going to just make a choice and see what happens. So I'm going to write the copper half reaction unchanged. So it's going to have aqueous copper ions on the left, solid copper on the right, with a cell potential of positive 0.34 volts. Now I'm going to reverse the rhodium half reaction. That would put solid rhodium on the left and aqueous rhodium ions on the right. But since I reversed that half reaction, now the cell potential changes from positive 0.80 volts. It becomes negative 0.80 volts. But I can tell this cannot be the correct answer, since if I combine a positive 0.34 with a negative 0.80, this would give me a negative cell potential for the overall reaction. So I can eliminate choice C with copper ions on the left and rhodium ions on the right, because that cell potential would be negative, and that would not be thermodynamically favorable. Now, for choice D, I'm going to just switch things around, which means I'm going to reverse the copper half reaction, putting solid copper on the left and aqueous copper ions on the right, and I switched the sign, so now that's negative 0.34 volts, and I'm not going to change the rhodium half reaction. So I have aqueous rhodium ions on the left and solid rhodium on the right. And that would give me a cell potential of positive 0.80 volts because I didn't change that reaction. Of course, I would need to multiply the copper half reaction by 3 so I could get 6 electrons lost. And then I would multiply the rhodium half reaction by 2 so I could get 6 electrons gained. Now that would give me an overall balanced equation which corresponds to choice D. But when I combine a negative 0.34 with a positive 0.80, I get positive 0.46 volts as my overall cell potential for the reaction represented by the equation in choice D. Remember, the criterion is not just a positive cell potential, but the one that has the largest magnitude for the cell potential will have the greatest thermodynamic favorability. So that makes choice B the correct answer to question 5 because it has the largest magnitude for a cell potential. And of course, it's positive. So choice B represents the reaction that has the greatest thermodynamic favorability. All right, now let's take a look at question 6. In question 6, it says a student sets up a standard galvanic cell with aluminum, Al, and zinc, Zn, as shown in the diagram below. And question 6 asks, the value of the standard free energy change, or delta G, for the reaction that occurs in this cell is closest to which of the following? Since we're dealing with aluminum and zinc, if we go back and look at that table, that means that we have to combine the aluminum and the zinc half reactions in such a way to produce the overall equation for a galvanic cell. So remember that a galvanic cell is thermodynamically favored with a positive value for the cell potential and a negative value for the delta G. So which of these two equations am I going to reverse so I can get a positive cell potential when the two half reactions are added together? Well, hopefully you can see that with a negative 1.66 volts, if I reverse that particular half reaction, that will become positive 1.66 volts. So now I've reversed the aluminum half reaction, putting solid aluminum on the left and aqueous aluminum ions on the right. So again, that's positive 1.66 volts. You can't have two reductions or two oxidations since I've already reversed the half reaction for aluminum, turning it into an oxidation half reaction. I'm going to leave the zinc half reaction unchanged. So zinc will remain exactly as written as a reduction half reaction. So the cell potential for the zinc half reaction remains as negative 0.76 volts. The next thing I'm going to do is get my electrons to cancel out. So 2 times 3 is 6. I'm going to multiply the aluminum half reaction by 2 so I can get 6 electrons on the right. And then I will multiply the zinc half reaction by 3 so I can get 6 electrons on the left. But as I mentioned earlier in this video, when we multiply a half reaction by 2 or by 3, we do not change the value of the cell potential. So those values will remain as positive 1.66 volts and negative 0.76 volts when I do these multiplication events. So aluminum will be 2, 2, and 6 for the coefficients from left to right, and zinc, it will be 3, 6, and 3. But notice I didn't change the values for the cell potential. Now I can add these two half reactions together, and the 6 electrons on the left can be crossed off with the 6 electrons on the right. And so here is the equation for the overall reaction. So 3 moles of aqueous zinc 2 plus ions reacting with 2 moles of solid aluminum, and it produces 2 moles of aluminum aqueous 3 plus ions and 3 moles of solid zinc. What's my overall cell potential? Positive 1.66 volts plus a negative 0.76 volts. And when I do that math, I get positive 0.90 volts. Now, this is not my correct answer. We're still looking for the value of delta G. But I can take the equation that was used earlier in this video from question 2, and I can turn the standard cell potential into the value of delta G. So what is my value of N? N is the number of moles of electrons transferred in this redox reaction. That would be 6. I can see 6 electrons lost, 6 electrons gained. So my delta G is equal to negative N, which is 6, then times the Faraday constant, 96,485 coulombs per mole of electrons, and then times the standard cell potential, which is positive 0.90 volts. Remember that a coulomb times a volt will equal a joule. So here's my unrounded answer on my calculator. I got negative 521,019. Again, the units would be joules. I'm going to round this off to 2 significant figures because 0.90 has 2 significant figures. Remember that 6 is an exact number, so that's not a measurement. So I get negative 520,000 joules per mole of reaction. Now I'm going to divide by 1,000 to go from joules to kilojoules. So my answer to this question would be delta G is equal to negative 520 kilojoules per mole of reaction. So that corresponds to A. So the correct answer to question 6 is choice A, negative 520 kilojoules per mole of reaction. All right, now let's take a look at question 7. In question 7, it says, which of the following is true for the reaction represented by the equation shown above? Let's focus on the sign of the cell potential for this reaction. The sign of the cell potential is negative. So what does a negative cell potential tell us about thermodynamic favorability? In topic 9.9, we know that if a reaction is thermodynamically favored, it would have a positive voltage or a positive sign for the cell potential. But here in question 7, this reaction must be thermodynamically unfavored because it has a negative sign for the cell potential. So to summarize, if the sign of the cell potential is negative, then the sign of the delta G for the reaction would be positive, and this would represent a reaction that is not thermodynamically favored. So we're looking for a positive delta G in question 7. So choices A and B indicate that the delta G is negative, so that's not true. The correct answer is either choice C or D with a positive sign for the delta G, indicating that the reaction is not thermodynamically favored. Now, what about the value of the equilibrium constant K? Well, if we look at topic 9.5, free energy and equilibrium, processes with a negative delta G, which would indicate a thermodynamically favored process, would have an equilibrium constant K that is greater than 1, favoring the products. But here, in question 7, we have a positive delta G. This reaction is not thermodynamically favored, so therefore the value of the equilibrium constant K would be less than 1, favoring the reactants, not the products. So since K is less than 1 when delta G is positive, that means that the correct answer to question 7 is choice C. So we have a reaction that is not thermodynamically favored. The sign of the cell potential is negative. The sign of delta G is positive, and the value of the equilibrium constant is less than 1. Now let's take a look at question 8. In question 8, it says, the electrolysis of an aqueous solution of potassium iodide, Ki, results in a chemical reaction that produces iodine, I2, according to the net ionic equation shown above. Now, if we look closely at the sign of delta G for this particular reaction, we can see that the sign of delta G is positive. That is a clue that this process is not thermodynamically favored. Another clue that this process is not thermodynamically favored is the word electrolysis. When you see electrolysis, that normally involves an outside power supply or a source of electrical energy, indicating that the reaction is not thermodynamically favored, and so an external power supply is needed. When we read the question, that's exactly what they're talking about. It says, what is the approximate minimum voltage that must be supplied to a 1.0 molar solution of aqueous potassium iodide to produce iodine according to the reaction shown above? So in this particular calculation that we're going to do for question 8, it's going to involve this equation that you have seen before in this video. Delta G is equal to negative N times F times the cell potential. But what I'd like to do is focus on the N for right now. So what is N? Well, the variable N represents the total number of moles of electrons transferred in the overall balanced equation for the redox reaction. So what makes this question a little bit different than ones you've seen before in this packet is that we are not combining two half reactions together to produce an overall balanced chemical equation. In fact, we are simply given an overall balanced chemical equation. So what I'm going to do is try to split this particular equation into two half reactions. I'm going to start with the iodine because that's the first chemical listed on the left side of the equation, but it's actually iodide, the I- ion. So how is iodine changing in this chemical reaction? It's changing from -1 to 0. So because iodine is changing from -1 to 0, that means that iodine is being oxidized in this reaction. What would the half reaction look like if I have 2I- changing to I2? Well, since oxidation involves the loss of electrons, I would have to put 2 moles of electrons on the right side of the equation to balance the overall charge as iodine is changing from -1 to 0. So that would be the half reaction involving iodine. Let me go ahead and write the reduction half reaction involving all of the remaining chemicals. So I have 2 moles of water on the left, I have 1 mole of hydrogen gas on the right, and I have 2 moles of hydroxide ions also on the right. So notice that to get that particular half reaction to be balanced properly, I would need 2 moles of electrons on the left. So I'm looking at an oxidation half reaction in which 2 moles of electrons are lost, and now I'm looking at a reduction half reaction in which 2 moles of electrons are gained. Notice that when these two equations, these two half reactions are added together, you would get a net ionic equation that matches what you can see at the top of this slide above this question. So now I've determined that 2 moles of electrons are transferred. So now I know that N equals 2. So 2 moles of electrons are transferred for every 1 mole of iodine that is produced in this reaction. Okay, so back to the equation, delta G equals -N times F times the cell potential. The only thing I don't know is the value of the cell potential. I'm expecting that the sign of the cell potential should be negative since this reaction is not thermodynamically favored. Watch out for your units because remember that a coulomb times a volt is equal to a joule. So I need to change positive 264 kilojoules into joules. That would be multiplying by 1,000, 264,000 joules. So on the left side of this equation, I've got my delta G. That's positive 264,000 joules per mole of reaction. And on the right, it would be N, which represents 2 moles of electrons transferred. I've got that negative sign, so negative times 2 moles of electrons times the Faraday constant, 96,485 coulombs per mole of electrons, but I don't know the value of the cell potential. All I know right now is that the sign of the cell potential should be negative, but I don't know what that value is. Let me go ahead and solve for the value of the cell potential for this reaction. I'm going to divide both sides of the equation by -2 times 96,485. So when I do that math, on the left side of the equation, I've got 264,000 divided by 2 divided by 96,485. But don't forget that negative sign is still there in the denominator. So my answer on my calculator is -1.368, and my units would be volts because joule divided by coulomb equals volt. I'm going to round this off to approximately 2 significant figures. I'll say -1.4. But what does that mean? If the cell potential is negative, it's not thermodynamically favored. If the cell potential is -1.4 volts, then the magnitude, 1.4 volts, that represents the minimum voltage that must be supplied from an external power source in order for this non-favored reaction to occur. So the fact that the cell potential is -1.4 volts, that means that 1.4 volts is the minimum voltage that must be supplied to produce iodine and get this reaction to proceed. So the correct answer to question 8 is choice C. Since the sign of the cell potential is approximately -1.4 volts, then I would need, at a minimum, 1.4 volts of energy to be supplied from a battery or some outside power source to get this reaction to occur. So again, the correct answer to question 8 is choice C. Now, let's take a look at questions 9 and 10. So we can see that both questions 9 and 10 refer to the following information. It says, a student sets up a standard galvanic cell with aluminum, Al, and silver, Ag. The cell potential is measured to be 2.46 volts, which corresponds to the value of the standard cell potential for the reaction represented by the following equation. So here comes question 9. In a second trial of this experiment, a student sets up an identical standard cell to the one described above. Then, a few drops of a 2.0 molar solution of aqueous sodium chloride are added to the half cell containing aqueous silver ions, resulting in the formation of a precipitate of solid silver chloride. So the question is, which of the following choices correctly compares the measured value of the cell potential in trial 2, again after that precipitate has formed, to the standard cell potential observed in trial 1, and provides the correct justification in terms of the Nernst equation. So we can see in the 4 choices, is the measured value of the cell potential in trial 2 less than or greater than 2.46 volts, which is the standard cell potential, and then is the justification because Q in the Nernst equation is less than 1 or greater than 1. So this question does fall under topic 9.10, cell potential under non-standard conditions. And as you can see highlighted on this slide, the standard cell potential corresponds to the standard conditions of Q equals 1. But as the system approaches equilibrium, the magnitude, that is the absolute value of the cell potential, decreases, eventually reaching 0 at equilibrium when Q equals K. But again, we have a precipitate that was formed in this particular trial 2. So any deviations from standard conditions that either take the cell further from equilibrium or closer to equilibrium, we've got to compare Q versus 1. Let's go back and look at the details of the Nernst equation. So the Nernst equation has a Q, which is the reaction quotient. That would be products over reactants. Now we don't count solids in the Q or the K expression, so the Q expression for this particular reaction would be written as follows. We have products over reactants, so the concentration of the aluminum ion in the numerator, and then the concentration of the silver ion cubed in the denominator. Now what happened in trial 2 was that a precipitate of silver chloride, AgCl, was formed. And if a precipitate of solid silver chloride is formed in the half cell containing aqueous silver ions, then the concentration of the silver ion will decrease. Now, where is silver in the Q expression? Well, as you can see, it's in the denominator. So if the concentration of the silver ion decreases, then mathematically that will cause Q to become greater than 1. So we are decreasing the concentration of silver, which appears in the denominator of the Q expression. So that means that Q becomes greater than 1. Now on this slide, this is something I had presented in my video that included topic 9.10, so non-standard conditions. And again, what happens when Q is greater than 1 would mean that the cell potential is less than the standard cell potential. And so when would Q become greater than 1? Well, either you have an increased concentration of product, or what happened in this example with that precipitate, we have a decreased concentration of a reactant. So how do we know we have a decreased concentration of a reactant? Well, take a look at where is silver ions located in this reaction. So silver ions, that actually is a reactant. So if the concentration of an aqueous reactant decreases, Q becomes greater than 1, and the cell potential becomes less than the standard cell potential. So that's going to be the answer to question 9. We're looking for a cell potential that is less than 2.46 volts, which is either A or B, but Q becomes greater than 1. So the correct answer to question 9 is choice B. When that precipitate formed, concentration of silver ions decreases, Q becomes greater than 1, and the cell potential becomes less than the standard cell potential. Now, question 10 is also going to involve non-standard conditions. Let's go ahead and take a look at question 10. In question 10, it says, in a third trial of this experiment, a student sets up a galvanic cell made from aluminum and silver, and the cell potential is measured to be 2.50 volts. Notice that that's actually greater than the standard cell potential of 2.46 volts. And so the question in number 10 says, which of the following is most likely to account for the observation that the measured cell potential in trial 3 is actually greater than the standard cell potential observed in trial 1. So again, this is going to fall under topic 9.10, cell potential under non-standard conditions, but we're looking for a reason why the actual measured cell potential is not less than, but is greater than the standard cell potential. Now, in my video for topic 9.10, this question came up in which it says the student observes that increasing the size of the electrode has no effect on the value of the cell potential. And the answer is that changing the size of the electrode involves changing the mass of a solid, but solids are not included in the Q expression. So since Q is not affected by this type of change, then the value of the cell potential is not affected. Let's go back and look at two of the choices in question 10. So choice A and choice B indicate that the electrode has a greater mass, but that would have no effect on the cell potential because solids are not included in the Q expression, so we can eliminate choices A and B. So the correct answer to question 10 is either going to involve changing the concentration of the silver ion or changing the concentration of the aluminum ion. And like we saw in question 9, here is the Q expression with products over reactants. So concentration of the aluminum ion on the top, and then concentration of the silver ion cubed on the bottom. So in choice C, it says the concentration of the silver ion has been changed from 1 molar, that would be standard conditions, to 0.010 molar. So if you're decreasing the concentration of the silver ion, as a result, Q becomes greater than 1, just like we saw in question 9, but if Q is greater than 1, then that would take you closer to equilibrium than standard conditions, and that would mean that the cell potential decreases. So it's looking like the correct answer is going to be choice D. So what happens when the concentration of the aluminum ion changes from 1 molar, which would be standard conditions, to 0.010 molar? What you're doing is you're decreasing the concentration of aluminum, and Q becomes less than 1. So back to that diagram that I showed you earlier as we were answering question 9. In this diagram, if Q becomes less than 1, then that will take you here. That will take you farther away from equilibrium than standard conditions. So when Q is less than 1, then the cell potential is actually greater than the standard cell potential. And this can happen in two situations. You either increase the concentration of a reactant, or what happened in choice D, decreasing the concentration of a product. Now, how do we know that a product concentration was decreased? Well, take a look at where aluminum ions are located in this balanced equation. They're on the right. So aluminum ions are actually a product. And so if the concentration of aluminum, or an aqueous product, decreases, Q becomes less than 1, and now the cell potential becomes greater than the standard cell potential. So again, the correct answer to question 10 is choice D. Decreasing the concentration of aluminum causes Q to become less than 1, and then the cell potential that we measure is actually greater than the standard cell potential. So again, correct answer to question 10 is choice D. Now let's take a look at question 11. In question 11, it says, An electroplating experiment is performed in which a bronze coin is immersed in a solution containing a complex ion that contains gold. So the elemental symbol for gold is Au. Electricity is passed through the solution, and a thin layer of solid gold is deposited onto the surface of the coin according to the reaction represented by the equation shown above. Now, if 4.00 amps of current is applied to the cell, the time required to plate 2.00 grams of solid gold onto the surface of the coin is closest to which of the following? So this question falls under topic 9.11, electrolysis and Faraday's law, and one of the important features could be perhaps to calculate the mass of material deposited on or removed from an electrode as in electroplating, or we could also calculate the time or the current. And you can take a look on the equation sheet. You can see that this equation, which is represented with the letters I, capital I, and then lowercase q and lowercase t, I can see what those variables stand for on the right side of this slide. So I is current measured in amps, Q is charge measured in coulombs, and then T is time measured in seconds. We can also see the Faraday's constant, 96,485 coulombs for every 1 mole of electrons. On the equation sheet, under the unit conversion section, I can see that 1 amp is equal to 1 coulomb divided by 1 second. And on this slide, which was something I had presented when I was teaching about topic 9.11 in an earlier video, the relationship between moles of electrons and moles of product formed in an electrolytic cell is related to the coefficients in the reaction. So if I look at the number of moles of electrons in the equation that we are given, and I can also see the number of moles of solid gold, there is a 3-to-1 relationship between moles of electrons and moles of gold. Now, how will the conversion factor be written as we're calculating the time required to plate 2.00 grams of gold? Well, that conversion factor could either be 3 moles of electrons for every 1 mole of gold, or possibly upside down, 1 mole of gold for every 3 moles of electrons. So I'm not sure yet. I'll have to wait and see. If I have 4 amps and the definition of an amp is a coulomb per second, then I either have 4 coulombs over 1 second, or I have 1 second over 4 coulombs. Now, with respect to which of these conversion factors I will use to do the calculations in question 11, I predict that it's more likely I will be using this equation or this conversion factor that has 1 second on the top and 4 coulombs on the bottom. Since the final answer should be in units of seconds, I would think that putting seconds on top would be an important part of my conversion factors. So let's begin with 2 grams of gold and see if we can convert 2 grams of gold into the total time in seconds. So I'll start with 2 grams of gold. I'm going to use the information from the periodic table to go from grams of gold into moles of gold. And the molar mass of gold from the periodic table is 196.97. So now if I convert from grams of gold to moles of gold, I'd like to get to moles of electrons. So it's going to be 3 moles of electrons for every 1 mole of gold. Now I can bring in the Faraday constant, so I can get from moles of electrons to coulombs of electric charge. So 96,485 coulombs of electric charge for every 1 mole of electrons. And then finally, 1 second for every 4 coulombs. That is the definition of 4 amps. So 4 amps would be 4 coulombs per second, but I'm putting seconds on top and coulombs on the bottom. When I pick up my calculator, this is what I'm doing. 2, or 2.00, divided by 196.97 times 3 times 96,485, and then finally divided by 4.00. So I got 734.8 seconds when I did that math on my calculator. I'm thinking that 3 significant figures would be appropriate as far as rounding off my answer, since 2.00 grams has 3 sig figs and 4.00 amps also has 3 sig figs. So I'll call this 735 seconds. Now let's look at the 4 choices for question 11. 735 seconds. That means that the correct answer to question 11 is choice C. We went from grams of gold to moles of gold, then from moles of gold to moles of electrons, then from moles of electrons to coulombs, and then finally from coulombs to seconds. So 735 seconds, correct answer to question 11 is choice C. Now let's take a look at question 12. In question 12, it says an external direct current power supply is connected to 2 platinum electrodes immersed in a beaker containing a 1.0 molar solution of aqueous copper nitrate, as shown in the diagram at right. As the cell operates, solid copper is deposited onto one electrode and oxygen gas is produced at the other electrode. An electric current of 2.50 amps passes through the cell for 35.0 minutes. The mass of solid copper that is deposited onto the electrode is closest to which of the following? So hopefully you can see how similar question 12 is to question 11. This definitely falls under the topic 9.11, electrolysis and Faraday's law. We have the mass of material deposited onto an electrode. In this case, it's solid copper. So the difference between question 11 and question 12 is that in question 11, we were calculating the time required to plate a certain amount of solid gold. Here, we're calculating the mass of the solid, but we are given the time. So we're given 35.0 minutes. What I'm going to do is consider the 2 possible conversion factors that would be connected to 2.50 amps. Remember that an amp is a coulomb per second. So if I have 2.50 amps, that would either be 2.50 coulombs for every 1 second, or I could flip that upside down, 1 second for every 2.50 coulombs. Now, because we're starting with time, I'm probably going to go from minutes to seconds, and then I think I would want to put seconds on the bottom. So I'm anticipating that I'm going to use this version of the conversion factor that puts coulombs on top and seconds on the bottom, but we'll go ahead and see how that works out. Now, one thing you might be wondering about is there a balanced chemical equation? And there is not. So let's consider, what is the relationship between moles of electrons and moles of copper? So what's the relationship between moles of electrons and moles of copper? Well, the chemical formula of copper nitrate contains copper ions and nitrate ions. And nitrate is such a common polyatomic ion that you probably have already memorized that. The charge on the nitrate ion, NO3, is -1. So we have 2 nitrate ions. Each of them has a charge of -1. So that means that the copper has a charge of +2. How does knowing that the charge of copper is +2 help me establish the relationship between moles of electrons and moles of copper? Well, because I have a charge of 2, that would mean that copper 2+ ions would gain 2 electrons to turn into solid copper. So that means that for every 1 mole of copper solid that is formed in this experiment, that would be 2 moles of electrons. I don't know necessarily if I'm going to put 2 moles of electrons on top and 1 mole of copper on the bottom, or if it's going to be upside down, 1 mole of copper on the top and 2 moles of electrons on the bottom, but we'll go ahead and wait and see how that works out. Let's go ahead and begin with time, and then we can get all the way to grams of copper. So I'm going to start with 35.0 minutes. There are 60 seconds in 1 minute, so 60 seconds on the top, 1 minute on the bottom. Now, let's put seconds on the bottom and coulombs of electric charge on the top. So 2.50 amps, 2.50 coulombs for every 1 second. Now I think it's time to use the Faraday constant, so 96,485, but I'm putting coulombs on the bottom and then 1 mole of electrons on the top. So I've gone from minutes to seconds, from seconds to coulombs, and now from coulombs to moles of electrons. So it's going to be 1 mole of copper for every 2 moles of electrons. The last thing would be to get to grams. So looking on the periodic table, the molar mass of copper is equal to 63.55. So we've gone from minutes to seconds, from seconds to coulombs, from coulombs to moles of electrons, and then from moles of electrons to moles of copper, and then finally from moles to grams. So when I pick up my calculator, I'll start with 35.0 times 60 times 2.50 divided by 96,485 divided by 2, and then finally times 63.55. And so on my calculator, I get approximately 1.7, so 1.729. I will round off my answer to 3 significant figures because 2.50 amps and 35.0 minutes have 3 significant figures, so 1.73 grams of copper. Considering the 4 choices in question 12, 1.73 grams of copper, that makes B the correct answer. We went from minutes to seconds, seconds to coulombs, coulombs to moles of electrons, from moles of electrons to moles of copper, and then finally from moles of copper to grams. So the correct answer to question 12 is choice B. Now let's go ahead and take a look at the last question in this packet. This is question 13. In question 13, it says, an experiment is performed in which molten lead bromide, which has the chemical formula PbBr2, the molten lead bromide is electrolyzed using an external power supply and inert electrodes as represented in the diagram above. Lead metal and bromine gas are produced according to the equation shown above. So question 13 is another example of topic 9.11. But what makes this question a little bit different than question 11 and question 12 is the following. In question 11, we were calculating the time involved to plate a certain number of grams of solid gold. In question 12, we were given the time and we were calculating the mass of solid copper deposited on the electrode. So in question 13, we're not calculating the time, we're not calculating the mass, we're actually calculating the number of amps. So it's going to be the number of amps in units of coulombs per second. So the question says, if 5.0 grams of lead metal is produced in a period of 1800 seconds, the average current flowing through the cell in this experiment is closest to which of the following? So look at all 4 choices. They have units of coulombs per second. So on the equation sheet under the unit conversions section, 1 amp is equal to 1 coulomb per second. So our strategy is going to be to first calculate the total number of coulombs involved with 5 grams of lead metal, and then take that number of coulombs and divide by the total time, which is 1800 seconds, because then we will get a number that has units of coulombs per second. Now, if you're wondering about the relationship between moles of lead and moles of electrons, let me go ahead and show you the chemical formula for lead bromide. Let's break it down into the positive and the negative ions in lead bromide. So the bromine ion, Br minus, the bromide ion, it's -1, and we have 2 of them. So if bromide is -1, and we have 2 of them in the formula, then the charge of lead is +2. So how does knowing that the charge of lead is +2 make that connection to moles of electrons? Well, what happens is that lead is being reduced from +2 to 0. So 1 mole of lead ions would combine with 2 moles of electrons to produce 1 mole of lead metal. So now we have a possible ratio involving 2 moles of electrons over 1 mole of lead, or we could flip that upside down, 1 mole of lead over 2 moles of electrons. So we'll wait and see how that works out. Let's start with 5 grams of lead metal. So 5 grams of lead, I think a good first step is to go from grams to moles. So from grams of lead to moles of lead using the information on the periodic table. So on the periodic table, 1 mole of lead has a molar mass of 207.2. Now we've gone from grams of lead into moles of lead. Let's go from moles of lead to moles of electrons. So it's going to be 2 moles of electrons for every 1 mole of lead. And we got that information by knowing that the charge of the lead ion was positive 2. Now let's use the Faraday constant to go from moles of electrons to coulombs. Remember, if we can get the total number of coulombs, then we can divide by the total time in seconds. So I'll pick up my calculator and I'll do 5.0 divided by 207.2 times 2, and then times 96,485. Now I'm not going to round off this number because I'm not done yet. So right now on my calculator I have 4,656.6, and that would be the number of coulombs associated with 5.0 grams of lead. So the total time is 1,800 seconds. So I'll do coulombs divided by seconds, and when I do this math, 4656.6 divided by 1800, I get approximately 2.6. So 2.587, I'm going to round off to 2 significant figures because both 5.0 grams and 1800 seconds have 2 significant figures. So 2.6 coulombs per second. Let's consider the choices in number 13. 2.6 coulombs per second, that would make choice D the correct answer. So the correct answer to question 13 is choice D. Question 13 is the last question in this packet, so we have now come to the end of the video. I hope that you found all of these answers and explanations helpful. Thanks for watching.